Hi guys, so today we'll go over convergent elite code questions. So some of the common tendencies that we observe, going to convert those tendencies into elite code questions. So one of the first things that we observe is the notion and the idea of fluctuating emotions, right? So we can convert this to a elite code question in the sense that if we have multiple different peaks of an array, can we capture the highest peak? So if we have, for example, 1, 2, 3, 4, 5, you can think of this 5 as a peak and then decreasing down to 1 and then going back up again to, let's say, instead of 5, it goes up to 7 and then it comes back down to, let's say, 1. So one of the questions that you can come up with is how many peaks are there in this array? So that is one question. How many peaks are there? Where peak is a definition of you have consecutive increasing subsequence, and then your peak is the max of that, or the last portion or the last element of that consecutive increasing subsequence. So how many peaks are there? Right? What is the largest peak? What is the largest peak? And we define largest peak as the difference between the end of the longest increasing subsequence, or the increasing subsequence and the minimum. So for this case, this peak would be 4. In this case, this peak would be 6. So what is the largest distance, peak distance? Right? This could be another question. And one of the ways that you can answer this is by identifying when these peaks end. And these peaks end when you notice a consecutive decrease, right? When you notice a consecutive decrease, or not necessarily a consecutive decrease, when you notice any decrease. So from 5 to 3, we see it decreases, and then as well as from 7 to 6. So that is a way to detect when you have a peak. We will also go over a couple of ASTAM related topics as well. So go over hazard functions. So hazard function is the probability function over the survival function. And it is also the survival function is e to the negative of the hazard function. And then another sort of main law of total, not law of total probability, but another essential concept here is the idea that the probability of x is equal to the expected value of the conditional probability of x conditioned on y. And now when we refer to this expected value, you can think of the probability itself as the value. So typically when you do expected value of x, you think of x as the value, and then you're multiplying the value of x by the probability that it is x, and then you're summing over that across all x's. In this case, that x or that value is now actually this conditional probability. And this probability is actually now the probability that it's actually y. So what is the probability that this actually exists? Well, this actually exists if probability of y, if we have y existing. So this is essentially the summation of the probability of x equals x given y times the probability of y across all x, y, all x and y. And so that's one of the common main formulas that we need to understand. And this comes up in many of the questions, like the root of it is really coming down to that the probability of the general x is the expected value of the probability of x conditioned on y. And now, if we also think about the concept of deductibles and how we can interpret that and view that in an integral format, we know that in the case of the client, right, they pay everything up to the deductible, and then the insurer takes uh, everything after the deductible, unless there is some policy limit. But in the case of just regular deductibles, if we have the expected value of, given that we have some deductible, so this would be considered the expected value of x, which is the loss, right, minus the expected value of the expected, or minus the expected insurer payment. Right, so this is the expected client payment, expected loss, expected insurer payment. Right, now the expected client payment, you can think of this is the integral from 0 to d. So if it's 0 to d, the client is paying all the total losses. Then if it reaches d, then the insurer is going to kick in and going to provide for those losses, and the max that the client pays is actually D. So this is the actually integral format of that. So that's a common thing to know. And then we also know that we also want to keep into note what the difference between mixtures are. So mixtures are when the probability density function is the weighted average of many different probability density functions. And then we also want to understand what a mixed random variable actually means. So a mixed random variable is different than a discrete mixture. A mixed random variable, that entire value itself is dependent upon two other random variables, and based upon their weights, explain how much each random variable contributes to this new random variable's value. This is different from saying that random variable y's entire distribution is this much weight of this distribution and this much weight of another distribution. And when you're even combining random variables, you don't even need to have the entire concept of weights. You can even have 2x plus 3y, where x and y are two different random variables. We also want to measure tail weight. So tail weight is all about when we're trying to model these large losses, how can we see what the tail of these large losses actually looks like? One is through calculating the raw moments. The fewer the raw moments, the greater the tail weight. Next is you look at the ratio of the survival function. Next, you look at the hazard rate and see how it decreases as x increases. Finally, you look at the mean excess loss function. Now, let's see, a couple of other things I want to go over. So, new distributions that we want to understand at a fundamental level is the idea of block maxima, as well as excess loss distribution. So excess loss distribution is the x minus d over x given x is greater than d. Now this is you're trying to model the tail. You're trying to model large values, you're trying to model the tail of the distributions. So how can we best approximate that? Through a generalized Pareto distribution. If your existing x variable is already a generalized Pareto distribution, then you already know that your mean excess loss will also be a generalized Pareto distribution. That's one of the properties. Another one of the properties is that any one of the continuous variables that you can see in the exam people will also, its mean excess loss function will also follow, it will also follow a generalized Pareto distribution. And one of the things to know about, in the same way, max block maxima. So max block maxima is a way of thinking if you have these different random samples, and these random samples represent the maxima of a random sample. So for example, let's say we have a sample of 100, like 1,000 students. 1,000 students. We divide these 1,000 students into 20 blocks of 50 students. And within each block, we select the max score of the student, if that, assuming that's what we're trying to measure. And then all of those, when we see the distribution of all those block maxima, that is what we refer to as the block maxima distribution, or the generalized extreme distribution. Now, now all of the common distributions will follow a generalized extreme distribution. That is one thing to note. Another thing to note is if we know that it follows a generalized extreme value distribution, then we can also conclude that the excess loss function, or the excess loss, follows a generalized Pareto distribution. So there is a relationship between these two distributions that are helpful when we're trying to intercorrelate these two concepts. Next, we look at probability generating functions and moment generating functions. So moment generating functions, they obviously determine moments. And the way that they determine moments is if you take the moment generating function, take the nth derivative of it, and evaluate it at 0, that is equal to the expected value of x to the nth. Same way when you have probability generating functions. Same way, same idea when you have probability generating functions. You're able to generate probabilities, and you're also able to generate the expected value of x times x minus 1 all the way to x times x minus 1 plus x minus n plus 1. So this is very useful when you want to find, let's say, for example, expected variance, where you can get the expected value of x squared and you can get the expected value of x. So that's that we also want to one of the main focus of this section is on aggregate models and aggregate severities and aggregate losses. And so this is really where the law of total expectation, law of total variance comes in, and we have a formula that you're able to derive for expected severity, aggregate severity, and variance of the aggregate severity. One of the other concepts to note is once we do find our generalized Pareto distribution, the second step is following the pattern and identifying the parameters that are specific to this distribution. So you can specify these parameters by looking at the slope of the excess mean loss function. You can specify these parameters by trying to match to the limiting distribution. So those are the two ways you can actually get these parameters. One of the other things I wanted to go over is the entire concept of maximum likelihood estimators. So when we have a distribution that we fit to our model, we have some estimator that we're trying to predict. Whether it's in the case of exponential distribution, gamma distribution, we have this some unknown quantity that we are trying to predict. We are trying to figure out what this unknown quantity is. So in the case of, for example, gamma could be alpha or theta, that we are trying to see what those values could be. Now, maximum likelihood estimation is one approach to determining those parameters based upon the observed data. So it's going to take the observed data and it's going to say, based upon this observed data that we have, what is the highest likelihood of this parameter being? What can it be? Right, of the highest likelihood. And so that's how we're able to, one of the ways that we can get maximum this estimator or this parameter, the value of this parameter. Next, if we dive into the so we talked about exact variance of maximum likelihood estimator. And if we think about now that we have our model, right? Let's say we have our model, we know what our MLE is, we have a good parameter chosen for our model, we have this model. Now we want to see, is this model actually a good fit for our data set? Now this is where many of these different tests come in. We have chi-squared, we have likelihood ratio tests, and we have the Smorov test, Kolmogorov-Smorov test. And now what these three tests are going to do is they're going to say, okay, we fitted this distribution. We think that this gamma distribution, this exponential distribution fits really well to this data set. Now what this hypothesis test is going to measure is if this distribution that we have selected actually models the data well enough. So that's our null and alternate hypothesis. Does this model that we have selected and chosen model the data well enough? And so for chi-squared, we have chi-squared goodness of fit test, and it's going to take the sum of the expected minus the observed squared over the observed, and that's your chi-squared test statistics. And that's going to see what is the observed counts, what are the counts that we should be expecting under this distribution, and is that difference actually significant enough for us to say that this model distribution is not valid? So that's chi-square test. We also have Kolmogorov-Smorov test. And what this test is doing is it's trying to see the difference between our fitted CDF and our empirical CDF if the max difference is significant enough to say that this model is not sufficient for this data. Finally, our third test is the likelihood ratio test, where we take one distribution, take another distribution, get the likelihood, log likelihood evaluated at those two parameters, see if that value is actually large enough to warrant that this distribution is a better fit than this other distribution. So at a high level, what we're doing is we're taking these distributions and testing to see if they are indeed a good fit for the model. We also have confidence intervals of these parameters. These parameters don't just come as is. We need to involve a certain level of uncertainty in determining the value of these. And so that's why we have confidence intervals for these parameters in the first place. Finally, we have discretization. Discretization is the entire idea that we may have a continuous distribution, but we can actually choose to discretize it by having these point masses, by having probability of x equals some value being actually a range that we can calculate through an integral. And so that's going to help convert our continuous distribution into a more discrete distribution. And this is useful when you're doing modeling related tasks and trying to understand if instead of just having a continuous distribution, does providing bins and does discretizing this continuous distribution actually have more predictive power? So you were able to test that in our model as well. So that's what I wanted to cover today. We'll see you in the next video.